Welcome to the 9th Andrew Chamblin Memorial Lecture. Previous distinguished lecturers in this series have included Stephen Hawking, Roger Penrose, and Michael Green. This year, we are very, very pleased that Frank Wilczek has agreed to give the 9th lecture today. Before we start, I'd like to say a few words about Andrew Chamblin, in whose memory this lecture series has been established. So here is a picture of Andrew Chamblin. He was from Amarillo in Texas. He was an undergraduate at Rice University in Houston, Texas, and came to England in the early 1990s to study relativity here. First of all with Roger Penrose in Oxford, and then as a PhD student with Gary Gibbons and Stephen Hawking here in the Department of Applied Mathematics in Cambridge. He was initially a student at St. John's College and later became a research fellow at Pembroke. His brief but very productive research career ended in his unexpected and sudden death at the age of 36 in Louisville, Kentucky, where he was an assistant professor of physics. Andrew's many friends and collaborators in Cambridge and elsewhere have established a fund to support a series of lectures to perpetuate his memory and promote the broad area of science in which he was interested. We in DAMT are very pleased to take responsibility for organizing this and have it as one of our important annual lectures. It is a pleasure to welcome today many of those who have established and given to the fund. Andrew's parents, unfortunately cannot be here today, commissioned a striking bust of Andrew, which is on display in the Department of Applied Mathematics and Theoretical Physics, and you can see it right here. I'd now like to move on to introducing our lecturer today, Professor Frank Wilczek from the Massachusetts Institute of Technology. Professor Wilczek is one of the leading theoretical physicists of our time. He has worked on a wide range of topics, ranging across particle physics, astrophysics, and condensed matter physics. He is known, amongst other things, for the discovery of asymptotic freedom, the development of quantum chromodynamics, the invention of axions, and the discovery and exploitation of new forms of quantum statistics in the form of anyons. His recent work has been following in the footsteps of James Clerk Maxwell, and he's been investigating color perception. For the discovery of asymptotic freedom, he received the Nobel Prize in 2004, together with his PhD supervisor David Gross and David Politzer. Professor Wilczek's title today is A Beautiful Question. Please join me in welcoming Professor Wilczek as the 9th lecturer.
Okay, thank you. It's a great pleasure to be here in Cambridge without the snow, and it's a great pleasure to be giving a lecture in honor of Andrew Chamblin, whom I knew and regarded as a friend. So my subject today is a beautiful question. It's this question: does the world embody beautiful ideas? Another formulation of that question is, can the world be regarded as a work of art? Because works of art are what embody beautiful ideas. So let me begin by talking about a crossroads of art and science, that is the science of perspective. It turns out that this will be a good opening into discussing the connections that have grown deeper over the centuries between concepts that we find beautiful and concepts that describe the world in its deepest structure. So, viewed from above, train tracks run in parallels, and then they never meet. They're parallel lines. But there are other valid perspectives, like this one. And in this perspective, the parallel lines do meet. A fascinating question then becomes a common question for mathematicians and artists is, what transformations can you make on an image so that they represent the same object looked at from different points of view? Right? Not everything will look like the same image, and there are very precise rules that you can figure out for what a given object will look like if you look at it from different perspectives. That's known as the subject of perspective in art and the mathematical discipline of projective geometry in mathematics. They're really the same thing. There are beautiful constructions in perspective or projective geometry. This really ought to be the first thing that high school students learn when they learn about geometry, how to make an accurate representation of a square tiled floor. I won't go through the details of this construction, but you should look into it. I'll show you a book where it's described at the end, and you'll have the joy of being able to see how very precise rules enable you to make valid perspective drawings like that. Thanks to people like Brunelleschi, artists, engineers of the Renaissance. People find this ability very beautiful, as well as fun, to make those drawings. You don't have to take my word for it. Just look at this. Soon after the development of the laws of perspective, you have masterpieces like this by Perugino, where St. Peter is getting the keys to the earthly kingdom of God. This was solicited by the Pope, and Perugino evidently had a great time playing with perspective in drawing this figure. You can see the tiled floor construction underneath as a base of the whole thing. Moving to the physical side now, that is the modern physical side, symmetry of equations, so the same idea but made abstract. I think we're going to have a problem with this. I don't want to join Unicam. Thank you. Symmetry of equations is the essence of our core theories, that is, our understanding of the basic laws of physics today. That is, we focus on equations that can be transformed in many, many ways, just as you can look at a scene from many different perspectives. The transformed versions usually look drastically different, but for special equations, they lead to the same consequences, just as different perspectives of looking at things. If you obey the laws of symmetry, of perspective, represent the same object. An example of this, and in many ways the insight that put physics on its modern course, was Albert Einstein's theory of special relativity, where the different perspectives that were allowed, the different ways of looking at the world that are supposed to be valid, are moving past a given situation with a constant velocity. That's supposed, according to the special theory of relativity, to make a transformation that does not change the laws of physics. So although things look different, if you're moving past at a finite velocity, a constant velocity, the same laws of physics apply to that transformed situation that apply to the original situation. That puts heavy constraints on what the laws of physics can be. That's the essence of the theory of relativity and what led to Einstein's new equations for mechanics that modified Newton's equations. So guessing symmetries, guessing different perspectives that can be valid, gives you constraints on the physical description that turn out to be constraints satisfied by nature. So inspired by that, physicists started to look for equations that can be written in many ways. Equations, technically, that have high amounts of symmetry. If we assume enough transformations, if we assume enough symmetry, that things look the same from many different points of view, now in terms of equations, we get led to very specific equations. Just as if you ask for an object that looks the same, if you turn around and look at it from all different angles, you get down to a circle or a sphere. So symmetry gives you very special objects. It also gives you very special equations. Physicists have gone wild with this concept, and nature seems to allow that. So perspective goes local. This is the key concept in our modern core theories of how the world works. So a vastly expanded concept of transformations, not just moving past things at constant velocity, as in the special theory of relativity, underlies the general theory of relativity, but was also anticipated or adopted or independently arrived at by artists in a form of art called anamorphic art. Here a picture is worth 1,000 words or more. Here's a picture of a typical work, or very fine work, I should say, of anamorphic art, where you can see this very interesting image made by taking a rather familiar image of a pillar and projecting it using a curved lens, or a curved mirror in this case. So those are the same objects. It's the same object, still a pillar, but it looks drastically different because you apply transformations to it. So to enable such generalized perspectives, in both cases, both in the case of anamorphic art and in the case of general relativity, we need to introduce media that allow the transformations. So in the case of art, we need reflecting mirrors or lenses that allow the transformations and can be said to be responsible for them. If we want to allow a very wide range of images of the world to all be valid, to all obey the same laws, we must introduce media, image-changing media, that are responsible for the change. And I don't know how to get rid of this permanently. We'll have to do it each time. So in art, the media are curved mirrors or lenses. In general relativity, the medium is a physical, a part of the world, a physical thing. It's what we call the metric fluid. This metric fluid has distortions. Those distortions are distortions in the structure of space, or how objects respond to the structure of space. It encodes distortions, which we call in physics lingo the curvature of space, and in fact space-time is important. It's important to treat both space and time together in this treatment. I call it a fluid, a metric fluid, because it flows. It's a fluid. It takes on a life of its own. It was introduced to make lots of distortions legitimate, but then the equations demand that it takes on a life of its own. It can support things like gravity waves, which are distortions in space and time that travel along, similar to electromagnetic waves, and take on a life of their own. So in this language, with these concepts, we can enunciate the yoga of general relativity, this fundamental theory of the world, in 2 steps. This is slightly refining and adapting a formulation of John Wheeler. John Wheeler says, matter tells space how to curve, space-time tells matter how to move. That's a little too poetic, but the spirit is right, we can refine it to make it absolutely correct by saying the metric fluid tells matter in its aspect as energy and momentum how to move, and energy momentum tells the metric fluid how to flow. You have to put in these qualifications because matter, as we'll see momentarily, has in its fundamental characterizations other properties besides energy and momentum, and so all those aspects have to be taken into account in figuring out how it affects various fluids and how the various fluids affect matter. So, to summarize, our theory constructions involve choosing what are the objects that transform. We call those substances, the things, the building blocks out of which we want to build the world. So elementary particles, in a sense. The sorts of transformations we want them to allow, the sort of changes in the image, the changes in the laws of physics we want to allow to still give a valid description of the world, and to implement big kinds of transformations, a wide variety of transformations, we have to add media that make the transformations or keep track of them. I don't know how you want to talk to it about it, but in any case, media that are responsible and enable the transformations. Those are the fluids, which in physics become force fields. So, the art of theory construction, which I've just described in words, can also be described in imagery, and we have this description of how that anamorphic image I showed you was made by the original artist. He had this column as an object, specifying the substance. He had an idea for how he would like it to look. So choosing the transformations he wanted to enable, and then design the enabling material here. So these artistic steps are exactly in parallel to how we construct our theories of the world. So far I've talked about shape and form, different kinds of perspective and space. Now I'd like to talk about color, which substantially enriches the discussion. So it turns out that to understand the non-gravitational forces, and we know of three of them, electromagnetism and the strong and weak forces, we need to introduce a new idea. We need not only space and time, but also extra dimensions that will represent more abstract properties of particles called colors and charges, and those things will be living in a property space. So the particles will be moving not only in ordinary space and time, but also in these property spaces. If that seems abstract, in a moment I'll make it very concrete. So the basic insight into color perception was due to this fellow, who also had the basic insight into the physical nature of color as electromagnetic waves, or light as electromagnetic waves. This is James Clerk Maxwell, son of Cambridge, but also Scottish. In this picture, he's holding this funny-looking device. This is his color wheel, his color top, I should say. And it really is a top. You're meant to swirl it around really fast. This is not only a toy, you can see a sort of playful grin here, but it's not only a toy, but a scientific instrument. Let me explain a little bit. So it has two bands of colored paper in annuli, and if you twirl really fast, the persistence division means that the colors of those bands get mixed, and you can see how many colors it takes on the inside to match any color on the outside. So Maxwell experimented by putting different amounts of 3 basic colors. This is oversimplifying a little bit what he did, but it's the spirit of it. 3 different colors on the inside and black to adjust the brightness. And he tried all different colors on the outside. And the question was, could you match all colors on the outside with 3 colors on the inside? With appropriate mixtures of 3 colors on the inside. And he proved that you could. And Professor Longair this morning showed me dozens of color bands like this that Maxwell, the actual ones that Maxwell used. It's quite amazing and inspiring. So with that, he made the case that human vision is trichromatic. It's based on mixing 3 different colors. Colorblind people, you can match any color they see, you can match their visual perception with just 2 colors on the inside. So they see a smaller space. That Maxwell's discoveries were the basis of modern color photography, which is based on 3 inks, modern computer graphics, which is based on 3 kinds of LEDs, and so forth. So with suitable brightness for the red, green, and blue, you can get any color on the inside. Okay, so now I'd like to connect that Maxwell work to the concept of extra dimensions, and then eventually to our basic theories of nature. So there's no denying the mystical appeal of the idea that there are extra dimensions. So here's a very appealing image. Wouldn't it be nice if the world were like that and we could sense those extra dimensions and imagine science fiction stories where we move in them and so forth? But if only we could experience them, wouldn't that be grand? Wouldn't that be exciting to experience extra dimensions? Well, we can and we do. This is a color cube. It shows in an image Maxwell's insight that you can get any color by mixing 3. And this, if you turn it around and look inside, you'll see all possible colors represented in this color cube as mixtures of blue, green, and red. And so, if you think about what instructions you give to a computer to tell you what to look at, you have to say at every pixel, at every position, X and Y, and at every time t, how much red to put there, and how much green to put there, and how much blue to put there. You'll notice that in this representation, the numbers R, G, and B look very much like the numbers X, Y, and T. X, Y, and T, X and Y are dimensions in the ordinary sense. T is an extra dimension to make space-time, and R, G, B are 3 other dimensions that we sense. And so really, this is what you see every time you look at a computer screen. You see this space, you see space and time, space, and of course, a series of different images means time, and at each place, you have to pick a point in the color cube. So really, extra dimensions are right in front of your eyes every time you look at a computer screen or the world. Now, when I talked about different ways of viewing space and time, I called that anamorphic art. There's not a word for the similar thing in color, so I made one up, which is anachromia. So Spaces of what are called, for historical reasons, but it turns out to be an uncanny choice, because the resemblances between these spaces and spaces of color, or perceived color, are just very, very uncanny. Property spaces of color charges are the essence of our core theories of the electromagnetic weak and strong forces. If you want to know about the electromagnetic properties of an elementary particle, all you need to do is specify the value of its electric charge. If you want to know about the properties of a particle as far as the strong interactions are concerned, so the properties of a quark that colored gluons respond to, what you have to specify is how much red, how much green, and how much blue color charge they have. We call the charges of the strong interaction colors, and in fact, we call them, there's no standard, but I'm trying to make a standard. We'll call them red, green, and blue. They are not perceptive colors, of course, but they're more like electric charges, and the formulation we have of the strong interactions, quantum chromodynamics, or QCD, is like electromagnetism on steroids. It's very much the same kind of equations. They're called Yang-Mills equations in this generalized sense when they're on steroids, as opposed to Maxwell's equations, but they're very similar in structure, except in the Yang-Mills equations, you have more colors, more different kinds of charge, I should say, namely 3 in the strong interactions, and that's what we call colors, but they're really much more like electromagnetic charges, and instead of one photon, you have 8 different kinds of photon-like particles that respond to and change those color charges. So it's electromagnetism on steroids. The weak interaction is similar, but based on 2 instead of 3 colors. So the property spaces of electromagnetic weak and strong interactions are here represented visually. A regular image, this is my daughter, by the way, a regular image has 3 colors, and so we get an accurate portrayal if we use quantum chromodynamics. If we use only 2 colors, we have to discard something. So here we discarded blue, and we get that. And here, electromagnetic, just to represent that there's only one charge, you get a kind of monochrome picture, all in green. So these are the kinds of properties. So specifying the amount of electromagnetic charge at every point in space and time will tell the electromagnetic field what to do. So this is how the world looks to photons. Specifying the 2 weak charges will tell the W and Z bosons, the corresponding particles for the weak interactions, what to do. So this is what the mediators of the weak interactions see. And for the color gluons, as I mentioned, they are sensitive to all 3 color charges. I should say that these are all distinct. There's only one electromagnetic charge. There's 2 weak charges which are different from the weak and strong, and 3 strong charges that are different from the electromagnetic and weak. But the number of them is 1, 2, and 3. So, in searching for equations that govern these kinds of charges, we can be inspired by the Einstein theory of general relativity, where he wanted big distortions of space to be possible. And that turns out to be a very happy thought, because that leads directly to our core theories of the electromagnetic weak and strong interactions. It's called local symmetry or gauge symmetry in the technical literature, but it's really this anachromic, large amounts of symmetry that depend on just doing different things at different points in space and time. So here, I've shown some anachromic deformations of an art. This is an underdeveloped art form, but I made some computer graphics images of taking this original picture of a candy stall in Barcelona with colorful candy and making rotations among red, green, and blue. So sort of changing the perspective in color space as opposed to ordinary space. Here, doing the same thing at all points, rotating things kind of in the bluish direction. And here you can see the more general distortion of changing things differently at different points in space. That's the analog for color spaces of the anamorphic transformations that we saw in space and time. And here's another one where I make more dramatic changes. Okay? As I said, this is an underdeveloped art form, but it has possibilities, I think. So as in general relativity, if we want to enable those kinds of transformations, we must introduce image-changing media that are responsible for them and can make the laws look the same even though the underlying substance looks like it's been transformed. And those media are the photon, weak-on, and color-gluon fluids. All the properties of those fluids are dictated conceptually by their role as being enablers of this kind of generalized symmetry, just as you get a complete theory of the gravitational field, general relativity, by demanding high amounts of symmetry for these kinds of position-dependent changes of perspective. So remember the yoga of general relativity? I hope you do, because we're going to get, the point is that you get a very similar yoga for quantum electrodynamics. Now the electromagnetic field, the photon field fluid, tells matter in its aspect as electric charge how to move, or translated into more mundane terms, electric and magnetic fields exert forces on electric charges and tell them how to move. So they contribute additionally to the gravitational fields, the structure of space-time, and telling things how to move. And the electric charge tells the photon fluid how to flow. Well, by now, you should be getting the yoga. So the yoga of quantum chromodynamics, same thing again. The gluon field tells matter in its aspect as color charge how to move, and color charge tells the gluon field how to flow. And I'll let you fill in the weak interaction version. The bottom line is that gravitons, photons, color gluons, and weakons, all the mediators of the fundamental forces of nature, are enablers and avatars. That is, they enable symmetry, and they are the physical residue of having enabled that symmetry, as well as concrete elements of reality. So they take on a life as particles, because in quantum mechanics, fields also exist in quantized versions, which we call particles. So, to our deepest understanding, the existence of all these particles and all of their properties flow from that conceptual function. The concept of local symmetry is so powerful, the media have to be so special in order to allow the laws of physics to look the same, starting from those very distorted setups, as they would in the original, that we get very precise equations for how those media have to work. So, coming back to our question, does the world embody beautiful ideas? Well, those are the ideas the world embodies. Are they beautiful ideas? Well, people found such dualistic yogas beautiful long before anyone knew that they govern the fundamental laws of physics. This idea that there's a substance that affects forces, and forces that affect substance. That's exactly the concept of Taiji, also known as yin-yang, but also literally translated as two fish, which the artist Xu Fahe, a modern master who contributed the image you're about to see, says is the essence of Chinese culture. So I didn't realize until he told me that this yin-yang symbol, which we often see portrayed in the West abstractly, really is meant to be two fish at play. And you can, in his portrayal, you see that they look like two fish with the eyes, and they look like they're having fun. So yin is substance, yang is force. That's the way they appear in Chinese philosophy. Each responds to and is shaped by the other, as this image portrays. And each contains an aspect of the other. So that's also true in physics. When you have fields, their quanta look like particles. When you have particles, their exchange also leads to forces. So forces and particles go together. They are different aspects, although substance, technically fermions, and forces, technically bosons, have also very different aspects, and it's the forces that are the avatars of symmetry, whereas the substance particles currently are just inferred from observations of matter. So, I can summarize everything that I've said so far in the form of an answer to our question. Does the world embody beautiful ideas? I showed you the evidence for the yin-yang concept, which turns out to be a basic concept that governs our theories of physics. We also saw the kinds of transformations, the kinds of image changes that we needed were changes in shape and changes in form, anamorphic and anachromic changes. Seeking to embody divine beauty, artistic creators anticipated those things too. For example, again, an image is worth thousands of words here. For example, this magnificent intuition of the divine embodies both changes in shape and exuberant changes in color that depend on where you are. So this is a grand mosque in Tehran, and you can see, and it's especially effective if seen through a fisheye lens, which distorts things even further, but you can see the shape, the play of shapes, and the play of color is something that people found beautiful long before they knew that this is how the world works at a fundamental level. So, does the world embody beautiful ideas? Yes. Beauty of concept, beauty of form, and beauty of color. All those things are directly reflected in the fundamental laws of physics. Things that people found beautiful before, we find again. Okay, how much time do I have left?
10 minutes.
Oh, okay. So that's how our current understanding of physics demonstrates, I think, very convincingly that the world does embody beautiful ideas. We'd like to see if we can build on that as a guide to the future. Can we guess more about the way the world works by relying on beauty as a guide to how things might function? So let me show you something that's not as beautiful as it could be, although I've just been arguing that it is very beautiful. This is a summary of our current understanding of physics. We have 4 fundamental forces, the strong, weak, and electromagnetic interactions, plus gravity. As I've said, gravity responds to energy and momentum. So without insulting Einstein, having said that, I'm going to ignore gravity. And the weak and strong interactions, because it's clear what that has to do with the substance and is universal. The strong and weak interactions, we have to specify what different colors of objects there are and what electric charges they are. And this is a complete inventory of the substances we need to make what's called the core theory or standard model of the strong and electromagnetic and weak interactions, and gravity comes for free. These are the conventional names in case you've seen those things. And now we have, for the last couple of years, also evidence that there's another substance, the so-called Higgs fluid, besides the quarks and leptons. So I'm going to simplify that a bit in order to have something that I can offer a compelling explanation of. Compelling, not necessarily true, but compelling. So I'm going to, for the moment, leave out gravity, but we'll put it back, we'll have something to say about gravity shortly, and take out the Higgs particle and take out the fact that this structure gets repeated twice over, so-called families. Then we get something pretty compact, considering how much it explains about the world. So let me go back a second. But there are still 3 forces, that's more than one. There are still 6 fundamental kinds of entities that are not related by motion in property spaces and have funny charges attached to them. So it's not as beautiful as it could be. It sort of reminds one, metaphorically, of a pattern like this. It's kind of scattered. It's not clear right away why it has this particular shape and form. But suppose we reorganize things and realize we could have reorganized that previous diagram into a meaningful pattern where it's meant to be something you can fold up into a dodecahedron. Sort of the fact that there are pentagons, that they come together, 3 in a corner, suggests to those with dodecahedral literacy that, that really what that earlier figure was meant to be was a dodecahedron, but some evil influence has kind of obscured parts of it and made it hard to understand. Could it be that the standard model is like that we have parts of it obscured, that the world is filled with Higgs-like fields, technically, that wreck the symmetry? And if we are clever and reconstruct what could be going on at shorter distances, we can find a unified structure that would explain, for instance, why there are exactly 12 dodecahedra, 12 pentagons in this case, because it was meant to be a dodecahedron, or in the case of the standard model, why the different substances were lopsided in exactly the way and had exactly those funny electric charges that we saw. Well, of course, I wouldn't be leading you down this garden path if I didn't have an answer. And the answer is, yes, we can. Right? In view of the time, I won't walk you through the details of this. It's not that complicated, but it does take a few minutes to explain. We can explain, the basic idea is that we can explain from an abstract pattern of symmetry exactly the colors and charges that we observe in the world. So we can start by something of very high symmetry that unifies everything, and by logical operations derive the colors and charges that we find in the standard model. So it's as if we can indeed find an underlying dodecahedron of which the standard model is a snipped up piece, or a bunch of snipped up pieces. So we have one entity then and one force. The one entity I've sort of shown you, although I didn't walk you through the details, that we can get all the particles of the core or standard model from a pattern of symmetrical ones. This is allowing all possible positive and negative charges of the different colors, and this is applying a rule to that to get the standard model. I should say, so everything is allowed here subject to the fact only to the constraint that you have an even number of positive charges, these solid circles. So that's an icon of building the world as we actually observe it from a mathematically ideal symmetric entity. And according to the idea that we can go from symmetry to a prescription for what the forces are, would give us a unified theory of all the forces based on color property spaces, that is, the strong electromagnetic and weak interactions. However, to validate that one force aspect, a major challenge remains. It's that one force would have to be a force that's equally powerful in all its manifestations. So really, if there's just one force, the power of the strong interactions, the power of the weak interactions, and the power of the electromagnetic interactions would all have to be equal. But as we view them, they're not. Now, the philosopher Karl Popper would tell us that the goal was to produce falsifiable theories. Here we have a theory that's not only falsifiable, but actually false. But that's not our philosophy. We don't give up. When we have a beautiful idea, we try to push it through. And fortunately, we learn from the Standard Model, importantly, that appearances can be deceptive in a very particular way. In particular, the apparent power of different forces can be deceptive, because, a deceptive representation of their basic underlying power, because, and this is what I got the Nobel Prize for, in what we call empty space and perceive as empty space or vacuum, there is actually a lot of spontaneous activity. This can be called quantum fluctuations, it can be called virtual particles, but in any case is spontaneous activity that's part of the quantum mechanical nature of matter, for which there's enormous evidence. What you're seeing here is what your eyes would see if they were capable of resolving 10 to the minus 14 centimeters and 10 to the minus 24 seconds. In fact, we average over that, of course, but with our computers, we can mimic it, and if these calculations have other consequences we can check, we should believe it, and they do, and we should. So this is what it looks like if you had such nimble eyes. So that means when we look at things, look to see what the structures of things at basic short distances, we're looking through a distorting medium, just as fish in turbulent water would be looking at things. You have to correct in order to see things the way they really are. To get sharp images of what's happening at short distances, you have to correct for the distortions. You have to design appropriate glasses. We can do that. Again, that's what I got the Nobel Prize for. And here's what happens if you do. If you take the electromagnetic, weak, and strong interactions as observed with their strengths here, and calculate corrections to get to shorter distances, which also correspond to larger energies, they almost but not quite meet. Again, Karl Popper would say, congratulations, but we want to move on. Can we rescue this situation? Well, beauty got us into this mess by suggesting we should try to unify everything. Can beauty get us out? It seems challenging because we've already unified everything. We got one force, one substance. What can we do? Well, one force and one substance still leaves two different things, force and substance, the two different parts of the yin-yang. So we can ask, is it possible that there's also symmetry that interchanges force and substance, so that those two things can also be transformed into each other without changing the structure of the world? That would tell us why, if you have one, you have to have the other, and why their properties are related. So we can ask if we can expand the equations of physics so that it allows transformations like that. Well, we can. This is called supersymmetry. The mathematics of it were developed especially by Julius Wess and Bruno Zumino in the mid-1970s, and it's become a very well-developed art in physics. It's enabled by introducing not color dimensions, not space-time that's distorted, but what are called quantum dimensions. Quantum dimensions are dimensions based on a different kind of number that satisfy, instead of x times y equals y times x, it satisfies x times y equals minus y times x. But that's the only difference. It's a big difference physically, because it means if you try to step into quantum dimensions, you can only take one step. That's, well. Anyway, to get equations that allow that kind of transformations, again, we have to add some extra structure, the quantum dimensions, and we have to expand the equations in such a way that they allow motion in the quantum dimensions, and when the particles we know about move into the quantum dimension, they turn into a different kind of particle. So every kind of force particle would turn into a partner substance particle. Gluons would turn into gluinos. We don't know what these particles are, but we don't know what their masses are, but we know their names. So the gluons will turn into gluinos, the photons into photinos, and so forth. And the substance particles would turn into force particles. So the electron would turn into the selectron, and so forth. So, as in our other theories, it's motion in extra dimensions that tells you what kind of particle you are. But this is a hypothetical new kind of dimension, quantum dimension, that we want to add to increase the beauty and completeness of our unification. The great thing is, if we do that, if we expand the equations, there are new kinds of fluctuations. There's more stuff that can fluctuate, new kinds of virtual particles. We have to redo the correction, and well, here's the giveaway, why I love Susie. If we redo the correction, allowing for those extra effects, now the unification of strengths of forces really works. And as a superb bonus, totally unexpected, we can also calculate how gravity is acting at these short distances and high energies, and it pretty much unifies also. We don't have a detailed theory of how to put all four forces together. We have a very detailed theory, well, reasonably detailed, of how to put these three together. But this is powerful circumstantial evidence, both for supersymmetry and for the idea that there should be a unified theory of all the forces. And we're close to it. So it's really fun to visit superspace, and an unforgettable experience. So that's what I wanted to say. I think I've probably slightly overflowed the time. But just let me say that for all this in more depth and much more, in July, you'll be able to look at this beautiful book. A beautiful question. I love this cover design. It's a peephole, and you open up and you see hidden beauties. Okay, thank you very much.
Professor Wilczek has agreed to answer some questions. If anyone has anything they'd like to ask, now is your big chance.
Oh, sorry, there's one right at the back. Sorry.
Hello. Mostly from the first section of your talk, I wanted to ask, just because I'm curious, whether or not you've heard of Leibniz's expression, the living mirror, with
No.
reference to the different fluids and the different types of transformations.
No, I haven't.
It,
But thank you.
it's
Yeah,
in the
please.
Monadology, I think.
I'd be very happy to learn
Yes.
about it. Yes,
Anyway.
thank you. Sounds. Yeah, I think there are real opportunities for collaboration and mutual enhancement between science and art opened up by these ideas. Yeah. Yeah. Any other?
You asked the question whether the laws of physics look like art, but I'm wondering, could we say instead that perhaps the way that we build our theories, we build them in a way that we build our art? How do we know that the theories, the laws of physics should be beautiful rather than just the theories that we build for the world are beautiful?
Well, these theories work. That's the main thing. They're built, I mean, it's one thing to propose a theory. It's quite a different thing to have it checked out as a valid description of nature. So this understanding of how the world works has been built up over centuries with input from many, many people. I think it's fair to say it really gelled in the later part of the 20th century when it all came together in this particular form, but it didn't have to, and it hasn't always looked that way. So at different points, the description of the world had perhaps different kinds of beauty, but I think not as much. All right. Here's another one. Yeah.
Thank you. Very beautiful presentation. But as an economist, all I can see is dark matter. Where does that fit in this colorful description?
Economics?
Not economics, but dark
Oh,
matter.
dark matter.
Not too different.
Well, we don't know yet exactly what the dark matter is. There are ideas that ascribe it to some of the particles we need to implement supersymmetry. So that might be another advantage of supersymmetry. There are other ideas, which I really like, that ascribe it to a different way of improving on our core theories that would take a little bit longer to describe. It's a better way of understanding why the laws look the same forward in time and backwards in time. This leads to a particle called axions that could also be the dark matter. Currently, we don't know which of either of these ideas is correct, but one or the other certainly would be a beautiful explanation of why there's dark matter. But at present, we don't know for sure. There are experiments underway to try to sort that out. Yeah.
Thank you. Regarding your exposition of the ideas involving absolute symmetry,
Yes.
how does entropy fit in with this?
Entropy is kind of an orthogonal idea. That's what I've talked about here is the basic laws that, roughly speaking, correspond to a reductionist, the base of a reductionist description of the world. I don't like the word reductionism because it suggests reduction, but actually it's an enhancement of our understanding. Newton called it analysis and synthesis, which I think is much nicer. So you analyze things down to basics and then build up. This is the bottom floor. This is as deep as we know how to go. Entropy is kind of an emergent concept that arises when you deal with complex situations involving many particles. It's profound, but it's a different branch of physics and philosophy than what I've discussed here.
Well, I think that's the end of the questions. I hope you will join me in thanking Frank
All right, thank
once more.